Hello world of Apache NATix RTS International Workshop 2024. I will tell you today about sport shooting lane control computer made with NATix, created together with my friends from Cover Sport Shooting Club located in Poland. My name is Tomek CeDeROM, also known as CeDeROM. I'm the independent ICT researcher, open source by heart. FreeBSD is my favorite operating system and NATix is my favorite real-time operating system. So I'm also kind of crazy inventor, creating tools, libraries, designs, devices, rapid prototyping, reverse engineering and stuff. In my free time, I really like skydiving. The sport is really good, and allows me to take rest from this computer world. It keeps my mind, fresh and focused, as well as body, the healthy spirit lives in a healthy body. Especially the extreme sports enable you to, react in a constructive way, to focus on the solutions, in a problematic situation. So that also is kind of useful skill in solving real life problems. So having this kind of, friends around is very inspiring. And we are sharing, together our skills. We are helping each other. So I'm usually the computer and electronics guy. So this project is kind of result of a, friendship and open mind to experimentation. So what's the problem? One of the locations has 10 lanes that are already around 20 years old. The company that created the system is not on the market anymore, and servicing, is really hard. Not to mention the design, the maintenance, where you don't have the replacement parts available is really hard. Increased, rate of failures in recent times, revealed this possibility that the whole system probably needs a replacement soon. So we decided, to create something on our own. Of course, we can buy very complex and expensive, system, but we just need something that will work, and provide one-to-one compatibility replacement. Because we are creating this system on our own, then we are able to add some new functionalities that were missing in the old system. We can design the modular, system that will be easily replaceable, upgradable, and open for all kinds of experimentation. So I wanted, and as most with my projects, we are using only open source components. The software libraries, tools, and the NATix is also open source with lots of different, drivers, functionalities. So that's the perfect candidate. So this is my first design, first device, first project made with NATix. Another problem are the components. So recent, supply chains problems revealed that it's not really good to use highly sophisticated and hard to get components. So we are using only commercial off-the-shelf, really easily replaceable, inexpensive, easy to find components. And with this kind of approach, with friends open for experimentation, we created this system. So how the lane works? There is a someone that wants to practice. There is a paper target attached to the car that is then operated with a electrical motor. The electrical motor is controlled by the lane computer, and the lane computer gets the directions from the pilot controlled by the user. In our case, we have the 3-phase 4 volts installation. The motor is also 3-phase motor with brake, or sometimes without brake, and the positioning is achieved by using quadrature encoder. So we can see how it looks in reality. The box is the control computer. This is the old system for comparison. We can see the cables, going inside. The cables, I can tell you, are screwed inside. So with that many cables, it's really hard to service, this kind of part. Imagine replacement of this kind of box. There is a 3-phase motor, using the rubber belts for the wheel. That, by the use of metal line, provides the traction for the car that we can see on the right side picture. And the target is attached, below the car. There is a grip. So positioning of the system can use quadrature encoder. Other systems use Hall sensors. So you can see on the left side picture the O-ring that is attached to the axis, and then this O-ring has 10 magnets that provide impulses to the Hall sensor. From the electrical standpoint, it works almost equally the same as the quadrature encoder. So our new device can use both Hall sensors and quadrature encoders. The other methods for distancing is may use laser sensing or time of flight, but remember the car moves really fast, so the information provided here needs to be really rapid, to provide the good feedback loop, as this is the real-time application. And we can see the pilot. Pilot is quite simple. There are two buttons. One uses the target desired range, and the other button, the green one, is used to move the target back and forth. And the LEDs above are indicating current position and desired position. So the block diagram of the new design we can see right now was designed with a modular approach in mind. And also everything had to be connected with using cables and sockets and plugs, because this is the experimental device, so we want easy maintenance, easy servicing later on, but at the experimental stage something might get broken, something might need quick replacement, so we need to be able to easily reconfigure the whole system. So the power supply is provided over the socket. There is a power switch, there is a motor control block protected by fuse. Computer, the electronic device called here the motherboard, is protected by emergency stop that shuts down the computer, that shuts down the motor control. Computer is also protected with easy accessible and easy to replace fuse outside the box. One also important part here are the power indicators. So the previous design didn't show really if the power was connected or not. The new design has two power indicators that will at first glance reveal if the external power is connected. Either the power switch, the main power switch, is turned on or off, so we will know if it's safe to operate inside the device to open it, and the other lamp shows the activity on the computer. So each of the components, the functional block has this its own connector, and the motherboard consists of power supply. Each of the functional block has its own, power domain based on DC-DC converter. So in case of failure, other blocks will be operational. Inputs, outputs are protected, with optical isolation. Then also we have the positioning control block, the CPU board based on Natix RTOS. There is a CAN controller UI with LED RGB stripes, or the SPI LCD screen, and the audio speaker. So the CPU board is also in a form of a dedicated separate printed circuit board, because if, for example, one MCU doesn't fit the requirements, then we can easily or gets burned, for example, we can easily replace that board with some other board. We can easily replace the board with different firmware. For example, this application really requires rapid servicing, so the disturbance in operations in here with this design can take around 1 minute, right, to replace something. So this is the first prototype that is already operating. We can see it resembles the block diagram pretty close. We can see the panel with the connectors, the high power relays to control the motor, the fuses, the power supply, and so on. And I will tell you right now how did that happen step by step. So the first challenge was to have the 3 power supply at home, which is not really common because we usually have one phase only with 230 volts. We need the 400 volts AC 3-phase connection, so I had to buy a power inverter. I'll also played with some plugs, different plugs and sockets for the power delivery. I decided to use this kind of plug that will use female connector, and it will be closed by design. That provided security, and in case the whole device need to be detached, no wires, high power wires will hang in the air. There will be just a plug that we can detach, attach, and it will be fairly safe to use. I also was verifying the control of the phases delivered to the motor, because the motor direction depends on how you attach the phases L1, L2 and L3. That provides the clockwise movement, and if you connect L2, L1, L3, that provides the counterclockwise movement. So that was the first challenge and experiment to see if we can operate this kind of motor at home. Okay, so it works. You can see 6 connections. Normally you will use the star or delta configuration, by connecting those connectors to the power supply. In our case, it was, I will tell you later on how the motor operates. So then I had to create the lane simulation. Of course without the car, of course without the wire, but just something that will resemble the target configuration. So there is a metal plate, there is a motor mounted on additional metal plate that can regulate the rubber stripe stretch, and there we have the traction wheel that use 2 slots. One is for the rubber belt from the motor, and other slot is used to mount the metal line that it's attached to the car, and by rotating the wheel we achieve the movement of the car. So another problem was the quadrature encoder. These are not really available anymore, and their mechanical design is kind of different than the modern ones use. So there was this kind of metal adapter on the slot, as you can see. I had a problem with obtaining these components, and I didn't really wanted to use hard to get components, so I researched the modern encoders, and I had to create some kind of adapter for that. The movement axis is attached to the encoder with use of clutch. You can see on the picture that sometimes this clutch was broken in the old systems, and this requires also 2 holes, one on the mounting part and the other in the adapter, because the clutch had to be screwed to the axis and to the sensor. So initial test was made with 2 metal plates, and some screws. That was really hard to maintain, and also it didn't provide any protection against the dust, because it's a closed place, but it's very dusty. So we need to invent something that will also provide some cover against the dust. And after some months, I couldn't find, the inexpensive CNC service, or someone that will design this. For me, my friend, hinted me that we can use, the plastic. So I created the prototype on the 3D printer. It turned out to be fine. And then my friend created the CNC with, kind of more resistant plastic. So this is the upgrade of the old system on the left hand side, and the right hand side we can see already the new system. The electronics was designed in KiCad, of course. The printed circuit board initially was created with rapid prototyping precision CNC machine. It's the 2 layers 2 sides printed circuit board, and when everything was ready, I ordered the boards from the factory, And then it was kind of fun, you know, to create 10 boards like that. You know, we can see the semi-smart pick and place machine, neural based, you know, self-sufficient. I'm really proud of that machine, but maybe one day I will be able to get, you know, the real one, pick and place that will allow me to create, you know, like 10 boards, 10 devices per day, or maybe 100 devices per day. So I recorded the whole process. I wanted to show you some better time lapse, but you know, like hundreds of hours, you know, compressed into 1 minute, that wouldn't make sense. So I will upload it to the YouTube. If you like, you can watch it. I'm not a YouTuber, beware. So then I had to create a casing. The metal casing wasn't really much more expensive than the plastic one, and it turned out it had a metal plate that could, you know, mount all of the components. This also gave us the possibility to replace everything, you know, inside once the device was mounted on site. One good thing here is the rivet nut. That's very neat, you know, solution. I recommend it to you. These rivet nuts are really great way to mount anything everywhere. Then I had to create holes, you know, in the casing. The manual version, as you can see, wasn't that good as expected, and also I had to create, you know, the cables with all of the connectors from the motherboard, from the components to the casing. It turned out, for example, that the plastic, you know, so-called industrial grade plugs were breaking very easily, so it was quite a lot of work with the cables. So then I decided to switch to metal sockets and metal connectors. They are far better and also not that much expensive. We can see that the power supply socket and the main power switch is located on another board, so they could be also replaced just in case. And the manual drilling, you know, of the holes in the casing, I replaced that with the metal panel that was beautifully crafted with the CNC machine, and then it's just, you know, attached on the screws. Also on the rivet nuts. One thing I would improve right now is not to create every single cable from the panel to the target. I would, in the next version of the hardware, I will just create a cable, you know, the ribbon cable, ribbon tape that will provide, you know, the single connection from the motherboard to the printed circuit board that will be located below, you know, here the panel, and of course the high power supply, the motor control socket, will require dedicated cabling, but this will save really lots of time and work. So right now we can see the upgrade. We are not using single, you know, cables that are screwed inside to the motherboard. They are unlabeled, you know, it's like 50 or several tens of those cables, so the servicing was quite painful. Right now we have the metal casing. Everything is using cables, connectors and sockets, so everything can be easily replaced, you know, or modified. The metal plugs, you know, as you can see, are doing well. So the last part to do is quite trivial. It's the pilot. There are pilots like this available already on the market. I just had to create the holes for the LEDs. That was quite challenging, so I invented, you know, to create a PCB that will provide the mask for drilling, and that enabled, you know, the precise drilling for the LED sockets. Also the LED board later on was screwed, you know, for easy replacement with these nice nuts that could be heated up, you know, melted into the casing, and that was quite elegant solution. Other components of the pilot were created with a 3D printer, and you can see the final version of the pilot, you know, on the picture below. So this is the old pilot on the left side picture, and the new pilot on the right hand picture. They are quite the same, provide the same user experience, nothing fancy. So this is the upgraded system. You can see the old system on the left side photo. and the new system on the right side photo. You can see that the power is connected with the power plug. There is a power switch that can, you know, power cycle just in case the whole system. There is a fuse socket easily available at the bottom, and the two lamps that indicate, you know, whether the external power is provided and whether the computer is operational. So you can see the test without the moving car and without the metal line yet. This is installed on the old components, so that proves the one-to-one compatibility. Also notice how fast is the motor and how fast, you know, the wheel turns. And this is the movie showing the car already attached and the system, you know, operational in the real world scenario. So we are using the motor that is dual speed motor. It basically consists two coils inside the single case. By connecting three phases to one set of three connectors, we have the low speed. It's around, depending on the construction, 900 RPMs, and connecting three phases to the other three connectors, we have the high speed. So it's around 2700 RPMs, depending on the construction. So the LEDs are showing, you know, the current state of the lane, where is the target, where is the car. Fast blink indicates fast movement, slow blink indicates slow movement. You can see that computer calculates and displays the current position of the car that wasn't present in the old solution. Okay, the NATIX part. So I did use the out of tree build, you know, so to keep the firmware code separate, the application code separate from the NATIX, and then this allows the easy NATIX upgrades. There are some automation scripts for configuration, build, flashing, so anyone else can easily, you know, make some modifications or build the firmware. I used the custom board definition based on the example. I used the ESP32, so thank you, Alan, for the example I could use. One thing I had to improve was the quadrature encoder. The default hardware provides 16-bit resolution, so I had to extend this resolution to, you know, higher number just to get, you know, the direct position number, not to process this information inside of the application. So there are several custom applications, you know, that are launched when the device starts. When we provide some input from the UART, then we will trigger the command line interface with some additional utilities for configuration, calibration, testing, logging, and stuff. And then, you know, if nothing like this is triggered, then we will start the default application. So I would like to also add the non-volatile storage, you know, for the calibration configuration. It is not required right now, but also I'd like to add Wi-Fi and Bluetooth for remote control, maybe synchronous work, internet platform that could, you know, read out the state, maybe possible failures and servicing request. CAN bus can provide the additional pilot implementation, maybe some additional sensors or interconnection with external systems. I'd like to play with MCU boot, of course, and some fancy display driver and LED RGB. So the problems and plans for future, these are mostly caused by the electromagnetic interference. You know, this three-phase high power motor is really big source of interference. High power relays are located inside the metal casing, so this is also source of the interference. And maybe installation, you know, a structure, it's metal, needs also good grounding. So everything, you know, vibrates, so this is the mechanical challenge. Over time the components were replaced, so we need to invent our own designed mechanical components that will be also inexpensive, you know, to manufacture. and multiply. It happens several times that the ESP32 hang on running motor. That requires the power cycle of the device. Although the watchdog was enabled, I'm not sure what's the cause, probably the MI. That needs some more investigation. In worst case, maybe I will try to use STM32 instead. NATix allows easy porting, of the firmware to different hardware. So STM32 is known to work in automotive industry, so maybe that's the case of MCU. I'm not sure yet. It's work in progress. So improved isolation, filtering, shielding, and also I'd like to try to use the power converter to control the motor, because so far we are using simple, one-to-one backward compatible design that is using power relays, but this does not provide, the full control of the motor. Also, the two-speed motor is quite expensive, and the replacement of several of these motors is quite expensive. So with power inverter, we could get, the smooth control of the speed of the motor, and also we could implement really cheap motor that should be sufficient in this case. So thank you very much for your time, thank you for your attention, and big thank you for Gregor and Nat for creating NATix. That's my new love. I tried several RTOS before, and I really like the, this rock solid, old school Unix approach on, microcontroller level CPUs. Kudos, respect, everything, all the best. Thank you for your attention.
Thank you, Thomas, for the presentation, an inspiring presentation. Let's see if there are questions in the room for Thomas.
Strategies that you found in NATix for this application, because we could argue that we could do without a real-time operating system at all, for example. Okay? And so just before we had a presentation for small apps and so on, and the portability, thanks to NATix, several advantages were great from that perspective. But from the perspective of your use case, share the advantages of NATix. Thank you.
So the question was, what is the biggest advantage of NATix? I guess that was the question. Well, the previous presentation showed the NATix is kind of unified ecosystem that can be used in various, environments. Other people here shows many different applications. So, from my standpoint, it's a really nice environment to work with, kind of BSD Unix that I really like, but on the microcontroller level. So of course it could be created on 8-bit MCU, written in assembly. But for example, then I couldn't have the internet connectivity, the Bluetooth implementation would be harder. In case of failure or decision to extend the design into a more powerful MCU, I would have to create everything from scratch. Right now I can easily port the design, the application, the firmware to totally different platform. I just need to see if the drivers are there. Probably they will be there, and maybe just need some adjustment or extension, like I did with the QEncoder. I don't know. There are lots of advantages.
Thank you for the explanation, Thomas. Do we have other questions? If there are no other questions, I would have a question. For this application that you realized, are you considering switching from the high voltage motors to a stepper motor assembly?
Well, so far it was one-to-one replacement, kind of retrofitting. Some of my friends I consulted with bigger experience in mechanical design, they showed me some stepper motors or some dedicated motors. It turns out they are more expensive, require dedicated power supply and also the control block. So I guess in this application, fairly simple three-phase motor, is enough. It's powerful, and maybe with control over the power inverter, it could provide smooth velocity control. That would be better characteristics than just switching with the relays. And what it turned out, that the biggest power spikes are generated over the power line and surrounding when the motor starts, but also when the motor changes speed. So, for example, if the car is moving fast and then we are detaching the power supply and then attaching power supply to get the low speed mode, then the kind of strong power spike occurs. So maybe if we had this, power inverter, the power spikes would be smaller. I don't know. Some people, told me not to use power inverter because they are killing the engines and they are generating the EMI. But in the current situation where I'm already facing, horrible EMI, I will try. Why not?
I see. Thank you very much for the explanation and good luck with the implementation.
Thank you, Ali. Thank you, guys.